Okay, so good morning and welcome again to Machine Learning Coffee seminar. So today we will have a presentation from actually two NeurIPS papers, and it's also given by two presenters. So Antti Hyttinen and Jussi Viinikka from the Department of Computer Science, University of Helsinki. And they will be talking about their paper titled On the Identifiability and Estimation of Causal Effects. And then today, the presenters wish that the discussion will be then held after the presentation so that they can keep the schedule there. But please go ahead, Antti and Jussi.
Okay, so yes, so this is on the identifiability and estimation of causal effects. I'm Antti, university researcher, and Jussi Viinikka will give part of the presentation. And we are from the Sums of Products research group of Professor Mikko Koivisto. So this is the outline of the talk. So the talk is based on two NeurIPS papers published last year and this year. The first in section 2 is about identifying causal effects via context-specific independence relations. And the second one in sections 4 and 5 is on Bayesian estimation of causal effects. And in particular, Jussi will present our state-of-the-art scalable MCMC sampling approach for DAGs. The remaining sections include background, research, and conclusion. Okay, so causal effects. We often need to make hard decisions, and often they boil down to make them optimally, we need to know some information about causal effects. So here is a picture that was around in Twitter this year, and this is on the wearing of masks and the coronavirus. So here on the y-axis, you can see the number of cases in a logarithmic scale, and on the x-axis, there is time. And as you can see, for different countries, those that do not have a mask wearing policy seem to have a rising number of cases, whereas those with the support for wearing masks have the number of cases seems to even out. But the correlation is not causation. It might be due to a number of factors. So the countries that have this mask wearing policy are, of course, quite different from the ones that don't have them culturally and also ethnically. Okay. So we would really need to know how large is the causal effect in order to make a decision whether to support wearing masks or not. And in the spring, we somehow came up with the decision not to support wearing masks. And there, I guess the reason was lack of evidence of their benefit. But there's a big difference in having lack of evidence of a benefit versus having evidence that there's an insignificant causal effect or that they are useless. Okay, so what are causal effects mathematically? Causal effects are probability distributions like this. So distribution of y given that you do x, and do x is the do operator of Julia-Pearl, where that means that we intervene on x and set it to a certain value. So you might have, for example, the probability of cancer if you start smoking, or the probability of corona infection if you wear a mask. Randomized control trials are, of course, a direct way to obtain these causal effects, but they are often infeasible. They might be unethical. I don't think there are still good randomized control trials for wearing masks. There's often issues with sample sizes, and they are recorded in different populations. I guess they are RCTs that don't find a link between smoking and cancer. So there, if you rely only on randomized control trials, you have very limited opportunity to gain knowledge for your decisions. Causal Bayesian networks are a type of causal model where causal effects can be rigorously defined. So a causal Bayesian network is a DAG, such as here, where the direct edges denote direct causal relationships from the cause to the variable to the effect. And then associate conditional probability distributions, which define stochastically how each variable gets its value based on its direct causes or direct parents in the graph. And importantly, dependence corresponds here to certain type of reachability in the graph, in particular d-separation. So if there are certain types of paths in the graphs, then the variables will be dependent in your distribution. And now on the right, we see what happens when you intervene on x. This means essentially that the value of x is determined irrespective of its natural cost set. So we cut out that edge, and in the factorization level shown below the graph, you just drop the factor of the intervened variable. And here you can nicely see that observing distribution of y given x is generally different than the distribution of y given to x, because y given x takes into account both of these paths, the direct path from x to y and the path through z, whereas when you do intervention, you only want to take into account the directed path, so the path from x to y. Then when you want to gain knowledge on causal effects, you can look at it in these 4 dimensions. So it depends on what data do you have. Maybe you have interventions on some of the variables. Maybe you have missing data. On the second dimensions, what kind of background knowledge do you have? Maybe you know the causal graph structure beforehand, maybe you don't. On the third dimension, it's a question of the assumptions you are willing to make. Are you willing to assume that your structure is acyclic? Maybe you have unobserved variables, unobserved background factors. This is this latent confounders. And on the other hand, if you assume there are no such things, then the system is causally sufficient. You might also have some parametric restrictions such as linearity. On the fourth dimension, the question is on what output do you really want? Do you want to decide whether the effect is identifiable? Maybe you want to really estimate it as well as you can. Maybe there are bounds, maybe you want bounds, or maybe you want to estimate some derived quantity of the due probability, such as the average causal effect. One setting in which causal effects have been particularly studied is this, the causal effect identifiability problem of Pearl. And there the idea is that you're given the causal structure as an input, and here I've defined it as a DAG, and then you're given a passively observed distribution over some of the nodes in the DAG. So note that some of the nodes in the DAG are in a sense unobserved, which is denoted here by the square node set. Your task is to output the formula for the causal effect over the passively observed distribution, or then decide that it's non-identifiable. Just to define what identifiability means here is that if the effect is identifiable, you can uniquely compute it from the input distribution. And if it's not identifiable, there are 2 different parameterization, for example, the Bayesian network in the background that yield the same passively observed distributions of the same input, but different causal effect, so different output. And in contrast to some literature, the idea has been here to develop a complete theory and complete procedures that tell you whether the effect is identifiable or not. So this problem is partly solved by do calculus, which consists of 3 rules. As you can see on the left, you can manipulate probability distributions and get rid of these do operators, especially in rule 2. And you can use these equalities whenever the graphical separation criterion or independence criterion on the right in blue happens to be true in the graph. So with these rules and probability calculus, you can derive expressions that prove the identifiability of a causal effect in many cases. Now here are two classic cases. In red on the left is the backdoor idea, where through this formula you can do this backdoor adjustment. So by summing over Z in this way, you basically take out the backdoor path through Z. This is a backdoor path because it has an edge into X, and you can take out the effect of that and untangle the causal effect. On the right, there's a bit more complicated formula and graph. This is the front door criterion, where you can also identify the causal effect. And it might be quite complicated to use the rules of do calculus, but gladly there's an algorithm, a polynomial ID algorithm that finds these expressions. It starts from the factorization implied by the graph and finds these expressions in polynomial time. And then when you have found this expression, if your causal effect is identifiable, the idea is that then you can use statistical and probabilistic modeling to calculate these terms accurately. So for example, if you have discrete variables, you would want to learn a discrete Bayesian network and use that to calculate the quantities in the formula accurately. In other cases, the causal effect might be non-identifiable, as here, where Z is unobserved. So here you cannot untangle the dependence through the causal path from X to Y and the confounding path through Z. And this graph here is an example of a graphical object called hedge. And whenever there's a hedge, the causal effect is non-identifiable. So whenever there's a hedge, there are these two different parametrizations that yield the same probability distribution, but different causal effects. And with this theory, Spitzer and Huang and Valtorta proved that ID algorithm and the do calculus, because the rules or the steps in the ID algorithm are all do calculus steps, they are both complete for this non-parametric identifiability problem here. And this table shows the recent or the current state of the art in identifiability. So the basic identifiability problem I presented is here in line 1, and it has been extended to various directions. In particular, if you look at rows 7 and 8, you have, or 7 and 9, you have selection bias and missing data. So the idea is that you describe in your causal graphs how the selection bias or how your data is missing, and with that you can then try to discover whether the distribution or a causal effect is identifiable. So if you look at the rightmost column, you see in color whether the problem has, whether there's a complete procedure for that problem. And as you can see, there are complete procedures for some of the easier problems, but for the later problems, there's no complete procedure here. For example, if you look at the row 8, where you want to estimate a causal effect, and what you get in are these bits and pieces of distributions from different studies. In that case, there's still no complete procedure available. You can still use do calculus and derive expressions as we did in this Tikka et al. Paper, but there's no completeness result. So one thing these non-parametric results do not take into account are context-specific independence relations, and that's the topic of our first paper, the first new research in this talk. So context-specific independencies given by Boutlier in the 90s are particular types of independencies where in the conditioning set you have certain assignment. So here X and Y are independent given Z equals 0. So this just means that when Z is 0, you can drop the Y from the conditioning part. And it still might be that X and Y are dependent given a different value of Z. And this is now a very natural independence restriction. Here are two examples. For example, your income might be independent of the weather if you're a clerk, but if you're a farmer, your income is probably dependent on the weather. So these types of CSIs have been extensively exploited in Bayesian network inference to make it faster and to combat the three-width that causes the computational complexity of Bayesian network inference, but they have only recently been used to make causal inferences possible. So we use the labeled DAX model of Pensar, Neumann, Koski, and Corander to model these context-specific independencies. The idea there is that it's basically a Bayesian network, but the DAX structure has labels on the edges, and the labels on the edges encode context where the edge is missing. So for example, here, the red label A equals 0 means that the edge from X to Z is always missing when A equals 0. This label induces this local CSI, so X and Z are independent given A equals 0, and these local CSIs imply global independencies and dependencies. For example, in this graph, X and Y are actually marginally independent, although there's a direct path with those, between those. So these types of local structures for conditional probability distributions of Bayesian networks have been somewhat studied, for example, using decision trees as the local model, but the benefit of this labeled framework is on many folds. So the labels allow for representation of the structure as well as the local and global structure in one picture. There are some theory on equivalence classes in these models, and also separation criteria can be developed based on the labels. So given this model, the causal effect identifiability problem turns into this. So instead of a DAG, you're given an LDAG, so a DAG with the labels, and then you ask whether the causal effect is identifiable or not. In our paper, we developed this calculus that solves this problem to some extent, called the CSI-do calculus, which includes many rules that are given here. And one thing to note here is that there's actually no do operator in any of these rules. And this is because the do operator, so breaking edges, reduces to probabilistic expressions, because in LDAX we have these labels that allow for deletion of edges. So interventions in this respect are only different contexts. And with that, we can do just probabilistic reasoning, derive probabilistic quantities from others, and identify causal effects this way. So these rules subsume the do calculus, although they don't include this do operator. And this is sort of, if you look at the original proofs of do calculus, this is sort of clear from there, but it is nice that the LDAC framework allows this inference to be done without the do operator. The bad thing here is that if you look at rules 5 to 8, there are these small letters which are particular assignments of random variables. So in this case, we need to do this case-by-case reasoning. So we need to reason on particular values of random variables instead of just random variables like in the regular identifiability case. And because of this, the identifiability problem becomes NP hard. Remember that it was a polynomial in the previous problem. So with this framework and so the calculus and search procedure over the rules of the calculus, we can get these new identifiability results. So all of these graphs, the causal effect of X to Y is identifiable. In the black, I've shown the formula also. So if we disregard the labels here, they are all non-identifiable causal effects, but with the labels, they become identifiable. And one might say here that even very few CSIs might be sufficient to turn a previously non-identifiable instance into identifiable. Okay, then that was the first paper, and now we are going to see a little bit of a different view, which is on estimation of causal effects, and in particular linear causal effects.
I'm really sorry to interrupt. I know you asked for the questions to the end, but there are a few really important questions in the chat.
Yeah.
So if you don't mind, I'll ask for some clarifications. Yeah. I don't know if Luigi, you got the reply already, but Luigi asked, how does the do operator differ from conditioning? So are you, Luigi, already happy with the explanation, or would you still like to get some clarification for that?
I mean, I think I said the last couple of slides, actually, you can see how, yeah, I mean, you can be formulated as a form of conditioning with these extended rules.
Yeah, so I think if I still highlight it in this picture, so conditioning sort of takes into account the influence through the background factors on X and Y. So here Y conditional on X would also take into account the influence that you get through this confounding factor Z, whereas if you do X, you only take into account the directed paths. And also, if you look at the formulas, conditioning would mean here in the factorization that you would, conditioning on X would mean that you divide by the probability of X, whereas in the factorization with the do operator, you drop the factor of X. So this is the difference. And on intuitive level, this means that whether you just observe somebody with the X feature or if you force the feature to be X. If you observe somebody smoking or if you force them to smoke. Okay.
Yeah, and then thanks. And there were also Suong asked, can the amount of non-identifiability be quantified?
I guess you could calculate how many graphs imply identifiability and how many don't. And I would say in many cases, the graphs that have identifiability, let's say from passive observation, they are rather special cases. So often the quantity might not be identifiable. But then if you have experimental data, as we see here in this table for some of the problems, then the issue might be different.
Okay, thanks. And also, can the labeled darks framework be scaled up to continuous variables?
Yes, so labeled darks are, as I present here, are for binary variables, and the extension to discrete variables is very straightforward. I guess if you want to do continuous variables, you might consider setting an interval on the let's say that the A is between 0 and 1, and then you have this edge disappearing. But I think a proper framework using all this is not developed. I think for decision trees, you can do this kind of continuous variables and intervals of those.
Okay, great. Thank you. That was all for now.
Yeah. Okay, how far we get? Okay, yes. So let's go to linear causal effect estimation. And there, so we are not assumed given the causal structure as input, but we observe a data set, passively observed data set, and we assume here that it's causally sufficient. So basically, in the model that produced the data, there's no these latent variables present. And the idea is, or the task here is to estimate the linear causal effect, which is given here. It's the derivative of let's say, the influence of different values of x to xj. This formula might be a little bit complicated, but the idea is that this is the regression coefficient of the cause variable on the effect if the effect variable is intervened on. And if you look at the Bayesian network with linear Gaussian conditional probability distributions, which imply these certain coefficients for the edges, the causal effect is a sum product of edge coefficients on the directed paths. So for example, for this DAG, the causal effect would be this sum product, which evaluates to minus 0.36. So in contrast to previous, there is only data, and we are looking at the linear case, so parametric restriction. The IDA algorithm of Matthews et al. Solves this problem followingly. So because we only have data, we have to do discovery first. So and Gaussian DAGs can only be identified up to the Markov equivalence class. So given enough data, we only know that the true causal structure might be one of these. Then for any fixed DAG, the causal effect is identifiable by a backdoor adjustment we saw earlier. And here it's just doing a regression on linear regression on X4 given the cost variable X1 and its parents, which are given here in the different graphs. So here, for example, you have X1 and X3, and including X3 in the regression model means that you intercept the paths through X3 and only consider the directed path from X1 to X2 to X4. So this method outputs a set of possible causal effects. So in this case, it would output this set of causal effects. And notice here that although the effect is unidentifiable, the unidentifiability or the non-identifiability is in very particular form. So we can actually identify this set of discrete values. And with this set, we might be able to, for example, bound the causal effect. Here you can see that 0 doesn't appear in the set. So the causal effect is non-zero. On the other hand, the causal effect must be between minus 0.74 and 0.49. So it can't be too large. And to make this method work, you only need to discover the possible parent sets of the cos xi, and you can do that, for example, via PC algorithm. And this is now a very scalable approach. You can do thousands of variables, but the accuracy may be limited, as I will show. So we set out to improve this method, and we took a Bayesian approach to do that. We published this beta approach this year in AAAI, which is essentially a Bayesian version of IDA. And the idea here is to get the posterior distribution of this causal effect Bji. And here we can employ a Bayesian linear regression of xi over xi and the parents of xi instead of a linear regression. And then this posterior employs Bayesian model averaging over DAGs. And because of this, causal effect estimate itself is constant for any graph with the same parent sets. So we can actually do this Bayesian model averaging by just model averaging over the parent sets of the cause. And this probability of a parent set given data can actually be computed exactly via dynamic programming algorithm up to, say, 20 variables and a bit more, but not for 30 variables. In the NeurIPS paper, we did a different approach to obtain the posterior, and this deviates a little bit from IDA, but follows the Bayesian paradigm more closely. So we get the posterior of the causal effect, and we do Bayesian model averaging over DAGs to account for the different the uncertainty in the graph structure. So here we sample the graphs G from their posterior using an MCMC approach called Gadget, which Jussi will soon present. Then we sample the coefficients B of the model, so the linear coefficients from certain distributions. They are T distributions, as we saw when you use a Bayesian Gaussian equivalent score equivalent prior. And finally, we can calculate the causal effect based on the coefficients through this formula, which is just the geometric sum formula. Remember that this causal effect was a sum product of edge coefficients. So you can get it through this. Okay. So this is what we get in the toy example. For IDA, you got this interval or this set of discrete effects. With our methods, that's called peeps, we get this posterior distribution of a causal effect. So as you notice, there are 4 peaks here. 3 of the peaks correspond to the estimates of the IDA. Note that each peak, there is a certain amount of variation due to low sample size, which was here 200. But more importantly, there's this 4th peak at 0, and this is due to the causal structures that were not the optimal causal structure with the data, but second optimal, and so although they are not the optimal causal structure, they are still highly likely causal structures, and then you get this added uncertainty due to the causal structure. So in our Bayesian approaches captures both of these types of uncertainties due to graph structure and low sample size. When we look at simulation results in larger scale, so here we had 20 nodes, and we looked at the output of each method and we compressed them to the mean value, and then we look at the mean squared error over all the marginal causal effects. And here we see the Bayesian methods just dramatically outperform the non-Bayesian ones. This peeps plus gadget is our method in this NeurIPS paper. And what we noticed that it's a bit better than the BIDA method that employs exact computation, because the estimator for the causal effect seems to be a little bit better. Then on the right, you can see a 107 node instance. So this approach scales to over 100 nodes, which is nice given that we do a very rigorous Bayesian approach. And for this plot, we ran the different methods for 12 hours. And here you can see the beeps and the gadget method that Jussi will soon present offer more accurate results than a previous MCMC approach for DAGs, together with this sampling for causal effects. So I should note that while we were doing this, there were also some similar suggestions for a Bayesian IDA by Kuipers and Castelletti and Cosonni, but they are all a bit different in some respect. Okay. So now Jussi will present the gadget, so the scalable MCMC sampling of DAGs that he developed.
Okay, so hi, I'm Jussi Viinikka. I will describe how we sampled from the DAG posterior for the Bayesian causal effect estimation method Antti just introduced. So our Markov chain Monte Carlo method starts off with 2 existing ideas. First, although we are targeting the DAG posterior, we run the chain in the space of root partitions. The idea is pretty simple and illustrated in this picture here. The root partition of a DAG is constructed by recursively placing the root nodes in the next partition part and then removing those nodes from the remaining DAG. So the root partition of this particular DAG, for example, has 4 parts. A root partition is compatible with many DAGs, since for a given node, it permits all the parent sets which satisfy these 2 conditions, which you can see on the slide. The parents must come from the previous parts, which we call U, and there must be at least 1 parent from the previous parts, which we call T. So in effect, we are collapsing the space of DAGs into a smaller space, which improves the convergence of the chain. Then on the other hand, each DAG maps to a unique root partition. So when for every sampled root partition, we finally generate one of the compatible DAGs, they come from the approximately correct posterior, which is not the case had we used some other collapsed sampling spaces like orderings. The score of a root partition is the sum of scores of all the compatible DAGs and which factorizes per node, as seen here. The score for each node is a sum of local scores permitted by the sets U and T, which I just introduced. Next, please. And the second existing idea that we took is that for each node we select some number k of candidate parents, meaning that we only allow the node to have parents from those candidates. Regarding candidate selection in this presentation, I will just mention that the aim is to select the candidates so that they cover as much of the posterior mass as possible. And in the paper, we give an exact algorithm for optimal selection when the number of variables is small, and then a number of heuristics that can be used when there's many variables, more than 20 or so. In practice, in most of the experiments that we ran, which we selected 15 candidates for per node. So in the following, we will just assume that we have assigned the candidate parents for each node. And once we have the candidates, can you go back? Once we have the candidate parents selected, we can pre-compute all node scores for of the form just seen, since they now only depend on these two intersections. So we only need O of 3 to the power of k space to store all scores per node. And the pre-computation then allows constant time evaluation of the node scores, which is a crucial feature for the MCMC chain, because we need to score one root partition on every step. Next. And we can actually do better once we realize that we can compute the node score through a subtraction, as shown here. So for a given node, we sum all the local scores where the parent sets are the subsets of U, and subtract the scores that didn't have a parent in T. This sounds maybe complicated, but it's actually pretty simple. And this brings the space requirement down to O of 2 to the power of k per node. And despite everything said so far, we actually do need to have a mechanism that allows parents outside of the candidates as well. So we build a separate data structure for this purpose. We need to do this because for some nodes, the found candidates may not be optimal, or the number of them might not be large enough to cover the posterior well, or the posterior landscape may contain large zero probability regions, which makes moving between root partitions inefficient for the Markov chain. So we would be stuck if we would just stick to the pre-selected candidates. So in gadgets, which by the way stands for generating acyclic digraphs from targets, we have a user parameter D, which defines the maximum in degree for the parent sets not contained in the pre-selected candidates. And how to make this scoring then efficient is to have the scores sorted. So when we are scoring a node in a root partition, we only need to accumulate a certain amount of those scores from the list until we are within some acceptable tolerance. So equipped with those two data structures, we can then run the Markov chain. The proposed moves within the chain are quite simple. Some root partition parts are either split or merged, or some nodes in different parts are swapped. And to mitigate the problem of getting stuck in local optima, we run M parallel heated Markov chains with the stationary distribution of the K chain proportional to what you can see on the slides, P to the power of K over M, where P is the unheated distribution. And then on every other step, a randomly chosen chain and its neighbor swap states with a certain probability. So finally, in the next slide, in post-processing, we sample a DAG for each root partition stored during the chain. And here we also have a novel per node data structure allowing fast parent set sampling, which requires investing some time and space in pre-computation. And to save space, we do this transposition trick where instead of sampling whole DAGs at a time, we sample one node at a time for each sampled DAG. So sort of a transpose of the normal. So as a summary, this is the gadget in in all of its steps. We have pre-processing, we have the Markov chain simulation, and then we have post-processing. That's about it.
Okay, thanks, Jussi. Then to conclude, so here are some research directions for causal effects. I think the research is going in the direction of, for example, employing an unknown graph. So when we don't know the graph, so in some sense, combining causal structure discovery and effect estimation. There are also these other views that I won't go into detail here. And just to conclude, so there is need to quantify the causal effects, and we need to do them from the data and knowledge we have. In the first paper, we showed that context-specific independencies allow for identifiability beyond due calculus. And on the second approach, we showed that Bayesian posteriors for linear causal effects are more accurate and characterize the remaining uncertainty. Yeah, Jussi presented the state-of-the-art MCMC posterior sampling approach for DAGs, and I would like to note that this is not limited to linear models, so this works with any decomposable score. For future work, it would be very nice to somehow prove the completeness of causal effect identification via CSIs, but this is much more complicated problem as it is NP hard problem than previous identifiable problems. We would also like to relax the assumptions we made to obtain the Bayesian posteriors, such as this linearity and causal sufficiency. There could be more work to do in the MCMC sampling approach, for example, on how to select the candidate parents and what sort of tricks can we still make to scale up the MCMC approach further. Okay, that's it. Thank you. These are the collaborators for this research.
Okay, great. Thank you. Do we have now questions from the audience still? So you can either write to the chat box or raise your hand. So I will give you the floor. Okay, so nothing yet. So I could ask, so this is also part of your future work, and you briefly mentioned that you have already some methods for selecting then the candidate parents. So could you say a few words about those?
Yes, maybe Jussi can explain what was the best idea to select the candidate parents.
Well, the best idea, I suppose, was the greedy approach where we start from an empty set of candidate parents, and then we first at the highest scoring candidate parents, and then the following parent following added parent is the one that has the highest score when it's combined to one of the already included parents. Is that more or less? I think Antti came up with this algorithm. So.
Okay.
Yeah,
so we tried several different heuristics based on several different structure discovery algorithms, and we have to somehow select the 15 parents now, which is rather a large number actually for sparse graphs, and this is currently the best, but there might be better ways still.
Yes, and we tried, for example, finding the parents with the PC algorithm or with hill climbing algorithm or greedy equivalent search, and so on. So there was, I don't remember how many we tried, but maybe at least 10, I guess.
Okay, great, thank you. And then Anna has a question also. Please go ahead.
Hello, so I'm a little bit far from all this machine learning, but so basically you suggest statistical method of defining that something is causation, right?
Mm.
But in reality, you kind of in real data science tasks, you don't need purely statistical methods. You just have domain knowledge, right?
Yeah.
How can you comment on that?
So the idea of this research is basically that the domain knowledge can be described by these input graphs. You might have, so here so the input is given as a graph, and this graph is your domain knowledge. And for example, if you have, let's say, medical treatments that have multiple steps, let's say surgery, physical therapy, and this kind of things, you can draw this graph based on your background knowledge. Then I guess if your instance is non-parametrically identifiable, as in here, you can use your domain knowledge of putting particular parametric distributions for parts of these terms in the formulas. But as I said, this is aim for a general and complete theory, not focused on one particular data set. So there are other literature that approaches the situation perhaps in the way you think, in particular in the potential outcome framework literature.
Okay, thank you.
So if you still have time, Antti and Jussi, there is still one question, and I guess this is now the last one. Do you want to ask it, Suang, yourself, or do you want me to read it?
Yeah, sure, I can do that. So Antti, it was a great talk. Thanks for presenting this. I was just curious how you generally think of updating posteriors on causal effects or on models, if in addition to like the initial observational data, which could be large, there's like an RCT data as well that comes in. Like if you want to combine the information from the two, how would you do that?
Yeah, so in the Bayesian approach, we assume the passively observed data set. There is so this is essentially score-based learning, and there is an approach by Cooper et al. On incorporating interventional data in this way, and the idea is then that you calculate the local scores and the distributions by basically you ignore, when you calculate the statistics for xi, you disregard all data where xi was intervened on. So in that way, you can build data from interventional experiments into the procedure quite straightforwardly. What I don't know is how well the MCMC chain, for example, mixes in these cases. Yeah, and this is sort of starts doing the inference again, so it doesn't really update it in the sense. I don't know how would I then update the posterior. I guess there would be ways following the Bayesian approach to do that as well.
Okay, so thank you for the great presentation, Antti and Jussi. So it was great that you could make it here and talk about your NeurIPS paper, and then waiting for the next year's NeurIPS paper then again and the new presentation then. But thank you everyone for joining, and see you again next week. Bye bye.
Bye-bye.
Thank you. Bye.
Thank you. Bye.